All right, so now I'm going to present to you Pantomime motion data anonymization using foundation motion models. And this is work I've done today together with Julian Todt and Thorsten Strufe. And our motivation was actually very similar to the paper we just had. We thought about the metaverse, and the idea of the metaverse is that we have a VR headset and we go into this virtual world and we can meet other people. And not just not just see them, but also we get a representation in this space as an avatar. So this digital avatar represents us, and it also acts and behaves like us because the headset or a different device records our motion, so how our body moves, and applies this as an animation to the digital avatar. And works a little bit like this. We have a motion capture suit, for example, and then for each timestamp, something's broken. For each timestamp, we get a single pose, and if you put these poses together, then we get a motion sequence, which you've just seen, now stopped. And with these motion sequences, we can then animate a character. Now, this gives us, sadly, a privacy problem because motion data itself is behavioral biometric, and we can use it to identify people and to do attribute inferences. For example, from walking data, we can identify people very well, and we can also infer attributes like age and gender. So there's an issue when we use this data for things like the metaverse. And our research gap, how can we get these animations and these nice motions that we want, because they greatly enhance social interaction in these spaces if we can transmit our nonverbal cues without giving away our identity. And there's some related work that already looked at this. For example, Nad or they did an anonymization specifically for Beat Saber. Sadly, this only works for Beat Saber data and requires also a large amount of data to train this. And then there's some, that's too early. Okay. Then there are some adversarial anonymizations, for example, from Marek Piast et al., but they only get so they train with a loss for the identification and one for the utility. However, they only get a symbolic representation in the end. And in overall, the naturalness, so that the motion looks nice to humans, is a bit hard to put into metrics. So this is not a good approach for us. Now, okay. Now, this is how the data looks like when it's not anonymized. Now, we first tried a naive approach and just said, okay, we're going to apply noise to it. And this you can, of course, do. But then, in the end, it doesn't look like a human anymore. So this is, for example, now so much noise that you only have 10% identification rate in the end. However, of course, you have a lot of dependency in the data, which is broken. For example, the position of your hand is dependent on your elbow, on your shoulder, on your torso, and so on. And then, of course, because it's a time sequence, you have a time dependency. And our idea was, okay, we still want to add noise. However, in order to do this, we first transform the motion data into a simple representation where we can do this without losing our utility. And we do this by using foundation motion models, which are large models which are trained on motion data. So think of them a bit of sort of dictionaries for motion data, and then perform the anonymization in their latent spaces. And why foundation motion models? So they're trained on these large sets, and they generalize also to other motions. So you're not just bound to the data that you have. And we specifically used variational autoencoders because in their latent spaces, similar motions are closer to each other, and they're also encoded as normal distributions, which later helps by adding the noise. And now, this is one, two. And now what we have is that we have the original pose, we encode it, we get the latent representation, and then we add normal distributed noise to it, get again a normal distribution, and then can put this into the coder and get a nice pose out of it again. And something's not right. Okay, this is now an anonymized example by us, which again then looks like a human walking, and now has the same level of privacy that we saw with the naive approach in the beginning. Now we did some evaluations on this. First off, we looked at the privacy utility trade-off, and for this we investigated it by using biometric recognition for the identification, and we used action recognition to quantify the utility. And we also performed a user study, and essentially we did an online survey where we showed these motion sequences to people and asked them, does it still look natural to you? And then they had to rate on a scale from 1 to 5. Now, for the privacy utility trade-off, what you can see here is that the identification accuracy. Then here we have the action recognition. And for both, we have here the chance level. So this is for the action recognition and this is for the identification. So ideally for the anonymization, this is the best we can do if we go down to chance level. And here we have the clear level performance for both action and identification. And what you can see is that we can reduce the identification by a lot, but still stay very close to the action recognition that we initially had. And by adding more noise, we get this nice trade-off curve where we can even decide to anonymize stronger if we like to. Then looking at our user study, we asked our participants to rate from very natural to very unnatural, how good they think the motion sequence looks to them. And for the original data, we can see that it scores close to very natural, so what you would expect. Then we have these direct noise examples that I've shown you in the beginning. Of course, they don't score well, but it's nice to validate. And this 10% means that it's down to 10% identification, or here 20%. And then when we look at our approach, we can increase the naturalness a lot and get much better results for that. All right, then we're already to the conclusion. So we were able to show that using these foundation motion models, we can get nice, natural, good-looking motion sequences out of motion data and anonymize them well. And this approach is actually quite general, and I believe it can also be applied to other complex data types. So if you have complex data which is hard to anonymize because you have a lot of dependency, then maybe consider this kind of approach. And then there's a link to our paper and to our code. Thank you.